Organic Chemistry, Chem 213, Exam 1 Material, Part 3. Substituent effects in aromatic rings. A substituent already present on a benzene ring has two effects. The first is the reactivity of the ring. Some substituents activate the ring and make it more reactive than benzene. The list here shows the reactivity increasing from left to right. We have phenyl, alkyl groups, nitrogen with carbon double bond O, so that would be our amide family, alkoxides, hydroxides, and NH2 groups. Included on this table, I went ahead and put that they are OP directors. We're going to be seeing the second effect that they have is their directive influence. And I like to have all these things together on one slide so they're a little easier to remember. So we will be discussing OP directors in more detail a little bit later on some other slides. Some substituents deactivate the ring and make it less reactive than benzene. Ammonium, NO2, CN, SO3H, carbonyl groups, those are all deactivators, and they're also metadirectors. We have two others that are classified as deactivators. Those are the halogens and also hydrogens. Now, they always put hydrogens in this list. It's a little confusing to me because all benzene rings have hydrogen on them. So we'll just add it to the list because we see that in the book, but we'll go ahead and not have to worry about it because all benzene rings are going to have hydrogens on them. But what I do want to point out of all the directors here, and again, the next couple slides will be in more detail, of all the directors here, activators, all activators are OP directors. All metadirectors are deactivators with the exception of halogens. Halogens are the only OP directors that deactivate the ring. So why do we care about if something on the ring is going to be making it more active or deactivate it? Well, that's one of the theory questions they might possibly ask you. Which of the following would make the ring more reactive or less reactive than benzene? So that's the one place we're going to look at this. But the other time we're going to look at this is when we want to do a polysubstitution. And when we want to put the third or fourth thing on a ring, then the activator or deactivator is going to influence where the third piece is going to go on the ring. We'll have some of those on some later slides. We'll see how this comes into play. The second effect a substituent on a ring, aromatic ring, has is it will tell the new guy where to go. So the orientation of the reaction. Of the three possible disubstituted products, ortho, para, and meta, they're not formed in equal amounts. The substituent already on the ring determines the position of the second substituent. Remember, the previous slide shows you which are OP directors and which are meta directors. Substituents are classified into three groups: ortho-para directing activators, ortho-para directing deactivators, meta-directing deactivators. Note there are no meta-director activators. Inductive and resonance effects control the reactivity and orientation in electrophilic aromatic substitutions. Looking into this a little bit more, inductive effects. Inductive effects are those effects that happen along the sigma bonds. Controlled by electronegativity and the polarity of the bonds in functional groups, if you have a halogen, a carbonyl group, cyanide group, NO2, these all withdraw electrons through a sigma bond connected to the ring. So we could see these examples here of the difference in polarity. We have a positive, partial positive charge here with a partial negative here. And what these do is they pull or withdraw electrons from the ring. Now, alkyl groups donate electrons to the ring. So these are the inductive effects. We have electron withdrawing groups and electron donating groups. Resonance effects, these are the electrons through the pi orbitals. Electron withdrawal and donation. The withdrawal or donation of electrons through pi bonds due to the overlap of the p orbital on the substituent with the pi orbital on the aromatic ring. Carbonyl, cyano, and nitro substituents withdraw electrons from the aromatic ring through resonance, while halogens, hydroxy or alkoxy, and amino substituents donate electrons to the ring. In your textbook, Table 16.2 lists some substituents, their reactivity, the orientation in the reaction, what type of inductive effect they have, and also their resonance effects. Problems. Devise the synthesis for each of the following, starting from benzene. What we're going to be doing is we're going to have a multiple step synthesis where we're going to start with benzene and we're going to have a disubstituted product. The first question asks us to synthesize meta-bromobenzene sulfonic acid. A hint would be this question is specifically asking us for the meta product. So what we need to do is make sure that the first thing that's on the ring is a meta-directing substituent. So I've drawn in the template from starting off with benzene to get a disubstituted product. What you'd want to do is to draw in the product first. Meta-bromobenzene sulfonic acid. Now what we need to do is take a look at both of the substituents and see if either of these are meta-directors. If both of them are meta-directors, then it doesn't matter the order that we put them on. But if only one of them is a meta-director, then that meta-director must be the one that is already on the ring at the second step, so it can direct the second guy to go in the meta position. Worst case scenario would be neither of them are meta, and that means this reaction is not possible. Bromo is an OP director, while SO3H is a meta director. So this is something you would have memorized, OP directors and meta directors. So this looks great. We happen to have a meta director. So that means in the middle step here, this is where I would have the meta director on the benzene ring. So when we undergo the next electrophilic aromatic substitution, bromo would go on the meta position. So at this point, all I have to do is fill in how do I actually do the reaction to get SO3H on the ring, and then how to get Br on the ring. SO3H requires SO3, H2SO4, while Br requires Br2 and FeBr3. Sorry, I threw that one in first. FeBr3. So I'm going to go ahead and clean this up and show you my digital version of this. It's a little bit neater. All right, I see here that I forgot to put heat in the other reaction, so be sure to include heat. Here's our SO3, H2SO4, benzene sulfonic acid. The only difference between my handwritten version of this one is benzene sulfonic acid is on the top where I had been have it written further down here, but they were both meta to each other. So this would be the exact same reaction. Devise a synthesis starting from benzene for para-nitrotoluene. So I have my template down. Now I need to go ahead and write out my product, NO2, and pair it to that would be CH3 for the toluene piece. We know that CH3 is an OP director, and we know NO2 is a meta director. It's asking us specifically for the para product. So the para, in this case orthopara director, must be on the benzene ring at this step first. I have the benzene products and reactants ready to go, so all I have to do is fill in how do I get CH3 on the ring and how do I get NO2 on the ring. Go ahead and pause the video, fill the rest of this in, and come back and check your work. Okay, I'm showing you my digital version because it's definitely a lot neater. The first step would be for us to put the CH3 group on our benzene. And again, if you notice, I happen to have my CH3 written on the bottom. On my handwritten example, it's the same thing as having it written here. This is a Friedel-Crafts alkylation. There's a minor secondary product of HCl, and typically you do not have to show this in a multiple step synthesis. If you wanted to add this, you'd put a plus sign and HCl beneath it. This is the nitration experiment. You can either write HNO3 or you can write it in the more organic version, HONO2. They're the same thing. And then because this is a CH3, which is an ortho para director, you only show the para product because that's all that it asks for. Sometimes for bookkeeping or people want to keep track, you could also say plus some ortho isomer if you'd like to do that, but you're not required to do that. The methyl substituent is ortho para-directing. The two isomers obtained in the final step would have to be separated. Usually the para isomer, in which the two substituents are the furthest apart, predominates. Is it possible to prepare meta-bromochlorobenzene by two successive electrophilic aromatic substitutions? Explain. Well, the previous two examples would be using two successive electrophilic aromatic substitutions. Well, let's take a look at what product we're trying to get. We're trying to get the meta-bromochlorobenzene. When we take a look at this, all halogens are OP directors. So this is a case where, no, we wouldn't be able to get it by two successive electrophilic aromatic substitutions. So the answer would be no, because both are OP directors. So when we had disubstituted, as we've seen in the previous examples, if something was a ring activator or deactivator, that didn't come into play. It was just the director piece of it. Well, now, if we want to go ahead and put a third thing on a ring, that's where the activity of the substituent comes into play. So let's look at trisubstituted benzenes. If the directing effects of the two groups are the same, the result is additive. So let's take a look at this reactant here. We have a CH3 group here and an NO2 group here. We know that CH3 is an OP director and NO2 is a meta director. The methyl group would cause the new substituent to go where they have it in pink here. It would go ortho to it, or para, but since there's something already there, it wouldn't be able to go there. And then the NO2 would also direct the new thing to go meta to it, which would be the exact same position that the CH3 wants it to go. So there's nothing competing. They both want it to go in the same place. The CH3NO2 starting material is symmetrical, so only one of the two sides would happen because they would be the same as each other, so we only get one product out of this. If the directing effects of the two groups are the same, the result is additive. When we have substituents with opposite effects, if the directing effects of two groups oppose each other, then the more powerful activating group decides the principal outcome. We also usually get a mixture of products. CH3 and OH are both OP directors. OH is a stronger activating group. So when we see the OH here would want the new reactant, in this case we're going to put a BR on the ring, would want it to go ortho to itself and para, but the para is already taken, so only these two spots would be directed. The CH3 would like it to also be ortho to itself, so it would be these two. When we take a look back at the directive influence, which is a stronger activator or weaker, we see that the OH is a stronger activating group. So it's going to win. It would be the major product. Remember, we usually get a mixture of products. I'm going to bring you back to this slide for just a second so you can see that I have listed here reactivity increases. So we have the CH3 here, the OH here. The OH is a stronger activator. And I have the same thing here, reactivity increases on our deactivator. Now, if we're starting off with a meta-benzene and we are trying to put another substituent, a third substituent on the ring, one of the limitations is it's too hindered to put something between the meta position. We see here that our CH3 is an OP director, so it would direct the new thing to go either ortho to it, here, or para to it. But between the CH3 and the Cl, that's the meta piece. This is too hindered, so this will not happen. So when you're figuring out where the third guy can go, it can never go in between the two metas that's already there. So how do you make an aromatic ring with three adjacent substituents? Well, you'd have to plan ahead and start off with the 1-2 situation, not a meta. You'd start off with an ortho and then bring on the third thing based on what kind of directing influence you have. for a one-step synthesis of 3-bromo, 5-nitrobenzoic acid. Which is a better starting material? 3-bromobenzoic acid or 3-nitrobenzoic acid, and why? How you would start this off is you'd go ahead and write out the product that we want, 3-bromo-5-nitrobenzoic acid, and then write out the reactants as two separate reactions because we have two separate reactants, and then look at what kind of directors they are. Go ahead and try this, pause the video, and come back and see how you did. All right, starting off with 3-nitrobenzoic acid, both of them are meta-directors, so both of them would want the new piece to go in this one position here. With 3-bromobenzoic acid, this is an OP director. Our halogen is an OP director, plus he's a ring deactivator on top of it. So he would want OP, he would want a product to go here, but also here and also here. And our benzoic acid piece would want it meta, which would be here, and this would give us pretty much a mixture of products, whereas a 3-nitrobenzoic acid would only give us the one product. So when we're rating them against each other, which would make a better reactant? The one that causes us to have the cleaner reaction, or the reaction that doesn't have so many multiple products at the end. Show how 3,5-dinitrochlorobenzene can be prepared starting from a disubstituted benzene. So for this problem, write the product. We already have the product named, and then you need to find, based on directive influence and activators and deactivators, which would be the best disubstituted reactant to start off with to get our trisubstituted. Go ahead and write out your reaction, pause the video, and come back and see what you have. Since chloro is an OP director and our NO2s are meta directors, it would be best to have both metas on the ring first. Devise a synthesis for the following using toluene as your starting material. Go ahead and pause the video and come back and see how you did. In this case, starting with toluene, you would want to put your meta director NO2 on in the second step. Both CH3 and NO2 would direct the new piece to go. So we have CH3 as ortho would want it to go here, and NO2 as a meta director would also want it to go in the same position because it's symmetrical, only one product is formed, and this would be the ideal way to make this product starting from toluene. If the chlorination were to be performed first, a considerable portion of the product would have the chlorine para to the methyl group. Also note that in the second step, both substituents direct the chlorine to the desired position. We're going to be switching gears here. This is no longer electrophilic aromatic substitution. This is nucleophilic aromatic substitution. Aryl halides are inert to both SN1 and SN2 conditions. SN1 are unfavorable because the aryl cation is very unstable. SN2, the halo-substituted carbon, is sterically hindered or shielded from the backside attack. What we're looking at for nucleophilic aromatic substitution reactions is an addition elimination to an activated aryl halide. In this reaction, what we're seeing is the Cl is going to overall be substituted with an OH group. Let's see how this reaction works. The reaction occurs in two steps and involves resonance-stabilized carbanion intermediate. The addition-elimination mechanism is shown below. The OH is going to bond to the carbon, and the pair of electrons that were causing the alternating double bond aromaticity here will actually be donated here. We have a carbanion intermediate, so we have this carbon here that has a lone pair of electrons plus a negative charge. That's what this is showing here. What's going to happen is the electrons are then going to regenerate the aromaticity. The pair of electrons that the chlorine had are going to be donated to the chloride, and it's going to be expelled. Nucleophilic aromatic substitution occurs only if the aromatic ring has an electron withdrawing group in the ortho or para position relative to the halogen where the anion intermediate is stabilized through resonance. The meta position does not provide the stabilization. The differences between electrophilic and nucleophilic aromatic substitutions. Electrophilic substitutions are favored by electron-donating substituents which can stabilize the carbocation intermediate. Nucleophilic substitutions are favored by electron-withdrawing substituents which can stabilize the carbanion intermediate. The electron-withdrawing groups that deactivate rings for electrophilic substitution, such as NO2, carbonyl, cyano, etc., those actually activate them for nucleophilic substitution. These groups are meta-directors in electrophilic substitution, but they're actually orthopara-directors in nucleophilic substitution. Benzyne. It's an intermediate that is highly reactive, and a triple bond is formed, and it's extremely weak. Nucleophilic aromatic substitution by a benzyne intermediate. What we're looking at here, we have Br going to be substituted by NH2 in this reaction. I have Br up here, and down here in the mechanism I have Cl. It's because either of these halogens would work. So I have chlorobenzene, and we have our OH minus. There's a minus charge here. I know it's kind of small, so you might want to draw that bigger. A pair of electrons are going to grab this hydrogen. The electrons that were holding the hydrogen on there are going to be given to the ring, and the pair that had the chlorine is going to have that chlorine pop off of there. So both HCl is eliminated. It's an elimination step. A triple bond, benzyne, is formed. When you draw a triple bond on a ring, we've had the alternating double bonds inside the ring. Well, the triple bond goes just right outside of the ring, if you note here. The second part of this reaction is our addition reaction. In this addition reaction, we're going to add OH with this benzyne piece. We will be able to convert from chlorobenzene to a phenol. Continuing on with different reactions of aromatic compounds, we're looking at the oxidation of aromatic compounds. The ring itself cannot be oxidized, but the alkyl side chains can. Many of the reactions happen at the benzylic position. These reactions occur with primary and secondary benzylic positions, but not tertiary side chains. This benzylic position right here must have an available hydrogen to leave. If this carbon right here is tertiary, again, we're not really looking at the benzene piece, they'll all have benzene. So if we're talking about 3 R groups on this plus the benzene, it's not going to undergo a reaction because this carbon right here must have an available hydrogen. That's why this carbon here has to have either 1 or 2 hydrogens for this reaction to go. We also tend to get a mixture of products. One of the oxidation reactions that a side chain can undergo would be the oxidation with a strong reagent such as potassium permanganate or sodium chromate if they have a benzyl hydrogen next to the ring. So for this oxidation to happen, we are talking about this benzyl position, and it must have at least 1 available hydrogen. Note that this one has 3, so yes, it does have at least 1. And what that's going to do is this carbon that's in the benzyl position is going to become a carboxylic acid, and because it's attached to benzene, it's going to be specifically a benzoic acid. Well, here we have a longer side chain, and we only have to look at the benzylic position. This carbon here, and I've explicitly shown you these hydrogens. Typically, when you see this reaction, they're not going to highlight them like this. They'll be written within the condensed structural formula. But I want you to notice that this benzylic does have a hydrogen available to undergo oxidation. What kind of product do you predict will happen? The benzylic carbon, if it has an available hydrogen, will undergo oxidation to a benzoic acid regardless of how many carbons are on there, as long as it has an available hydrogen. Here's our benzylic carbon. Does it have an available hydrogen? It does not. Remember, we are specifically talking about the benzylic position, not its neighbor. Whether it has hydrogens, it's this carbon that must. So this would be no reaction, no change. For this example, we have the exact same situation we had up here. So this one does not have an available hydrogen to undergo the oxidation. But I have two other carbons on my benzene ring that do have it. So what do you think? Do you think both of them will convert? One of them? None? As long as on a benzene, the benzylic position has an available hydrogen, and we use this set of reagents, yes, it will become a carboxylic acid, even if you have more than one. Another reaction we can do with the side chain of a benzene is we can brominate it. This compound here is abbreviated NBS, and you're definitely allowed to use NBS there. I do want you, though, to have NBS in its structure in your group of compounds or functional groups that you need to know. Most of the time, in fact, very rarely will you ever see this drawn over. You'll always see NBS over the arrow, and that's what I'd prefer you to do. Now, there are a lot more things involved in this reaction. This pH means it's a phenyl group, and we also have CO2, which means we're talking about C double bond OOH, and we also have CCl4. This reaction occurs only at the benzylic position. This carbon right here has to have an available hydrogen for this reaction to happen. And what's going to happen is we're going to substitute one of the hydrogens here for a bromine. And it will only, under these conditions, the bromine will only go to the benzylic position. So at this point, I'd like to compare bromination reactions. We've actually now seen 3 of them, and I'd like to bring them all together. So we have the same starting material here. I have NBS, bromine with either heat or light. I put heat. And then we have Br2 with FeBr3. I'd like you to go ahead and complete all these reactions, pause the video, and come back and check your work. NBS and these other reactants, what's going to happen is only at the benzylic position, I'll have a substitution of Br if the benzylic position has an available hydrogen, and this one does. You would get one product with bromine substituted on the benzylic carbon. Br2 and heat or light, bromine is going to attack an alkane, or the alkyl piece, and it can actually form multiple substitutions. Let's take a look at our products. You would get in this reaction 3 products, and you would be required to write all 3. We could have the bromine go to the first carbon, the benzylic carbon. Bromine can go to the second one, or it can go to the third one. You would get 3 products. If you're doing a reaction that you only wanted bromine at the benzylic, this would be the set of reagents for you to use. Br2, FeBr3, those are the reagents that attack the aromatic ring in an electrophilic aromatic substitution. Our side chain here is actually an OP director, so you don't get 1 product out of this, you actually get 2. Reduction of aromatic compounds. Aromatic rings are inert to catalytic hydrogenation under conditions that would normally reduce alkene double bonds. So we can take advantage of this by selectively reducing an alkene double bond in the presence of an aromatic ring. Here's an example. We have a carbon-carbon double bond here. This set of reagents reduces this carbon-carbon double bond. Everything else remains the same. The carbon-carbon double bond is now gone. An aromatic ring can be hydrogenated under conditions of a platinum catalyst with hydrogen gas at very high temperatures, or we can also use a very powerful catalyst such as rhodium on carbon. What happens in these conditions, again, notice the 2000 psi, 25 degrees, ethanol, platinum, and hydrogen. Under these reactions, we are able to actually reduce and get rid of these carbon-carbon double bonds. Reduction of aryl alkyl ketones. The aromatic ring activates a neighboring carbonyl group. The reaction is specific for alkyl aryl ketones. dialkyl ketones are not affected. Ketone is converted to an alkylbenzene by catalytic hydrogenation over palladium catalyst. Let's take a look at the final product here. Here we have a propylbenzene. In fact, technically it's a 1-propylbenzene. They should add that to the name because they're using the common name, and the IUPAC would be 1-propylbenzene. Down here we have a mixture of products of a 1-propylbenzene and a 2-propylbenzene. If you were wanting to do a reaction where you would not get a mixture of products, then you would want to go in this direction. The top reaction is written because you get 100% of that. The reaction on the bottom is actually a Friedel-Crafts alkylation, and the reason why it's showing a mixture of products is, if you recall back in the part where we learn about Friedel-Crafts alkylations, is there's rearrangement possible, and we do get a mixture of products. So they're actually at the end of this chapter showing you a reaction we saw at the beginning and tying it to a new reaction, the reduction reaction we learned at the end. So this is another comparative reaction. In your textbook, after chapter 16, they have a brief review of all the organic reactions and mechanisms for the beginning half of the textbooks, chapters 6 through 16. This is a really good review and a great summary for you to look over that you will need for the rest of the second semester. I highly suggest writing a reaction summary for you to review from these pages.